Okay. Okay. So we are very happy to have Sbierski talk to us on the uniqueness problem for space-time extensions. Great.
Thanks, Eric, for the introduction and also for the invitation. So it's the first time that I give a talk by writing on the iPad, so I hope everything works out. And if you have any questions, please do shout, since I only see you as a very small window. So please make yourself known if there are any questions. So yes, I'm talking about a recent paper of mine, and which is about the uniqueness problem for space-time extensions. Let me start with a literature result by Piotr Kruschel, which is now from 12 years ago. So let me run you through the theorem. So he starts with a smooth D plus one-dimensional Renzi manifold. Like so. And for the theorem, it's important that the dimension of this Renzi manifold is at least 2 plus 1 dimensional. So the theorem does not hold for 1 plus 1 dimensional Renzi manifolds. And then we have this concept of a smooth boundary extension. And so the concept is here that we have another D plus 1 dimensional Renzi manifold M tilde G tilde with boundary and a conformal embedding such that the image. Sorry, I wanted to draw this slightly different. So that the so let's say this here is the manifold M, and we have a conformal embedding iota tilde, which attaches here a boundary to the spacetime, but such that we only attach a boundary to the spacetime. Yeah, so this is this condition here. We only attach a boundary to the spacetime. And here, if we have the metric G here, then this is a conformal embedding. So here the metric G tilde will be something like G with a conformal factor. And we have another conformal embedding iota hat. Like so. And also here the metrics, they are conformally related. And now we have an anchoring curve. This is what I would call it. So we have a null geodesic gamma in the original spacetime, gamma, such that the curve gamma in the conformal boundary extensions also has a limit point. Here p tilde and here p hat. And also we assume that the null geodesic in the conformal boundary extension meets the boundary transversally. And then the statement of the theorem is that we can then find open neighborhoods of p tilde and p hat, u tilde and u hat, together with a smooth diffeomorphism id, which goes from u tilde to u hat, such that this smooth diffeomorphism maps the point p tilde to p hat, and also that here in the region of u tilde without the boundary, so the region that lies in M, such that here the identification map id is just given here by going up I tilde and going down iota hat. So what is important here for this, or the reason that we have to restrict to dimensions d bigger to 2, is that the statement of this theorem is just false for d equals 1 for conformal embedding. So you can find counterexamples of conformal boundary extensions which don't have the same smooth structure in 1 plus 1 dimensions. However, here I've stated everything in the smooth category, but Piotr also mentions that everything remains valid for G tilde and G hat in C11 log. And so we also only need that the boundary extensions M tilde and M hat, that these are only C21 log manifolds with boundary. And then the statement is that then the identification map, this smooth diffeomorphism, which relates u tilde and u hat, that this is then only C21 log regular. So in the rest of the talk, I'm mainly interested in isometric embeddings. Here, the motivation of this theorem, also of attaching smooth boundaries, is partly due to, for example, what this theorem gives you is that the differentiable structure of functional infinity is uniquely determined. So, for example, you can't find a different conformal boundary extension of an asymptotically flat Lorentzian manifold such that the differential structure at functional infinity is different. And so here the language that one uses is always of attaching just a smooth boundary. And this is also why conformal embeddings are interesting. And the reason that the theorem does not extend below regularity C11 log is that the proof crucially exploits null geodesics. And so we can only go to C11 log. One thing here in this theorem I want to elaborate on next is the importance of needing this, what I call an anchoring curve, this null geodesic gamma, which has a limit point in both extensions. So let me tell you why this is necessary. So about the importance of the, what I call the anchoring curve. And so there is a very fundamental counterexample, and I think many of you will be familiar with this one. This is the so-called Misner spacetime. And so the manifold is given by 0 infinity cross S1, here with t and phi coordinates, and the metric is given by this line element. And so we have here this cylinder. This here is the boundary at t equals 0. And so we have this, these two families of null geodesics, the past right-going ones, and what you can see is that they wrap infinitely often here around the cylinder when they approach t equals 0. And similarly for the past left-going ones, and they also wrap around infinitely often here when you approach t equals 0. And so the first extension which you can construct is by straightening out the left-going null geodesics. And so you introduce a coordinate v equals phi minus log t. And then the line element takes this form. And so what we have done here is we have straightened out the left-going ones. So they intersect transversely. Now the boundary here at the boundary here at t equals 0. However, the right-going ones, they still wrap infinitely often around the cylinder. And so they don't have a limit point when you approach t equals 0, but the whole surface, the whole S1 t equals 0 is an accumulation curve of the right-going null geodesics. So this is my first extension, I'm tilde. And then, of course, I can construct a second one by straightening out the right-going null geodesics. So I introduce a coordinate u equals phi plus log t, and then my line element takes this form. Yeah, and so now I've straightened out the right-going ones and the left-going ones. They wrap around infinitely often and asymptote towards the hypersurface t equals 0. And so this is an example. I mean, note that both of the extensions which we have constructed, they are both analytic. However, the extensions are completely different. So here in this extension, I have that the blue null GD6, they have a limit point, while in this extension, the blue null curves, they don't have a limit point, but they only have an accumulation curve. And so in particular, you see that the C0 structure already of the extensions is very different. Another way how you can see this, and also what I should mention is that both of these extensions, they are maximal. So in particular, you can't extend this space-time here, this extension, in another region, so that the red curves would also have limit points in the extensions. Since I mean the red curves, they already have here like a whole accumulation curve. So you can't make the extensions bigger. And so what I said, that they have very different C0 boundary structures. This also, when we look at the identification map, which maps the original space M in M tilde to M hat. And so the identification map here from M tilde with TV coordinates into M hat with TU coordinates takes this form. And you see, of course, that when t goes to 0, log t goes to minus infinity. And so you see that this identification map doesn't have a continuous extension to t equals 0. And so this example of the Mismar spacetime shows that if you want to get like a uniqueness theorem for extensions of Lorentzian manifolds, or boundary extensions of Lorentzian manifolds, as in Crucial's case, you need to have an anchoring curve. Yeah, since here in this example, you don't have an anchoring curve, you don't have any curves which have limit points in both spacetimes. So this is like a necessary condition, and this is very beautifully also elaborated on in Piotr's paper. So now let me make a slight shift in perspective, and I will tell you about the main result I want to present. And so the shift in perspective consists of in not talking about boundary extensions, so where I just attach a smooth boundary to the spacetime, but I want to talk about actual extensions as Lorentzian manifolds. So here gamma is a regularity class, like C1 or C2 or Lipschitz. And so a gamma extension of a Lorentzian manifold Mg consists of first a Lorentzian manifold M tilde G tilde, which has the same dimension as M. And now the metric is gamma regular. And then an isometric embedding iota, which maps the original Lorentzian manifold M into M tilde, such that it has a non-trivial boundary in M tilde. Yeah, and let me emphasize again, unlike Crucial, I'm only interested in isometric extensions. And so now the question is, we have now our Lorentzian manifold Mg with two extensions, iota tilde and iota hat. And so the picture would be something like this. Here you have M, and here you have the first extension M tilde, and this here would be the image of M in M tilde, and here we have another one, M hat, and this is the image of M in M hat. And so the question now is, do the extensions agree here on the boundary? So the motivation for studying whether the extensions have to be the same here at the boundary, for me, mainly comes from inextendability proofs. So the statement I'll present later, this is something that I need for proving that certain spacetimes are inextendable in a certain low regularity class. But I do think that this this question is also of independent interest. It's like analogous to the classical problem of extensions of functions in Rn. And I mean, there, if the extension is continuous, you trivially have that the extension is unique at the boundary. And another aspect, another motivation for studying this problem also comes from weak singularities in general relativity. So like where you have an extension in a certain low regularity class, but you can't extend it in a higher regularity class. And then the question is this low regularity extension uniquely given, or can I actually construct various low regularity extensions? And one pertinent example is, of course, the Cauchy horizon in perturbed Kerr black holes, for example. So this is the shift in perspective, that we don't just look at smooth boundaries which we attach to the spacetime, but extensions. Let me tell you now two issues which crop up when we make this shift. So the first one, it's the most important one, is that in general, if I try to use Crucial's result, that the closure here of I tilde M and I hat M, that these are not smooth or C21 log manifolds with boundary. So in general, of course, the boundary can be arbitrarily rough. So take, I mean, even when you have a smooth metric, so just take a subset of Minkowski spacetime, and if it has a very rough boundary, then well, the extension, the boundary and the extension also has a very rough boundary. And let me also mention that even if you have one extension in which the boundary is smooth, then you can think, okay, perhaps I can now apply the result. But I mean, in the result by Crucial, the assumption is that any other extension with a smooth boundary also agrees. So, for example, you already have the question, okay, I have one extension in which the boundary is smooth. Can I have another extension in which the boundary is rough, and then the geometry there is different? Yeah, so this is a question that I would need to answer. And another point, it's like a minor point, but even if the boundary is smooth, that then this closure might not be a manifold with boundary. And what I have in mind, you can already see from like a trivial example where you take the manifold M to be a subset of Minkowski spacetime minus 1, 1 cross R. Yeah, so the metric is minus dt squared plus dx squared. And then, of course, you can have one extension where you extend it just to all of Minkowski spacetime, but you can also have one extension where you identify this boundary with this boundary so that you get like a cylinder, right? Yeah, S1 cross R. And so then in this extension, you have, or the boundary and the original spacetime lies to either side of the boundary. So this would not be a manifold with boundary. But this is more like a technical point. And then finally, the last thing that I would like to address that goes beyond the work of Crucial is, can we go below the regularity C11 log, which was the limiting regularity for the last literature result. So the answer to see is that yes, we can go to local Lipschitz, but not beneath. And now let me first address the point A and the point B. So the point A I will address by not looking at general Lorentz manifolds, but I will restrict myself to Lorentz manifolds which are globally hyperbolic. And I will give a result that characterizes the future boundary of globally hyperbolic Lorentz manifolds. And I will show that the boundary is at least Lipschitz regular in a suitable sense. So let me come to this, to the statement. So in this proposition, let me again run you through what this proposition says. So we start here with our Lorentz manifold M, and it suffices that it has a local Lipschitz, a regular metric. I assume that it's time-oriented and globally hyperbolic. And I assume that I have C0 Warlock, a local Lipschitz, extension M tilde. And as I told you, local Lipschitz extensions will be the roughest ones we consider. Beneath that, the results will be wrong. And here, let's say the image of M and M tilde looks something like this. Yeah. Then again, we have our anchoring curve gamma, and recall the example of the Misner spacetime. So if we want to have any local uniqueness statement, then we need an anchoring curve. And say here this curve in the extension goes to this point, P tilde. It has this limit point P tilde, which lies in the boundary. And here I've drawn the case that can occur that the original manifold lies on both sides here of this boundary point. And the statement is then that for all delta there exists a chart phi tilde. So here we have this set U tilde, and I have a chart from this set into this Cartesian product of interval minus epsilon 0 cross minus epsilon 1 epsilon 1. And D here is the dimension of the Lorentz manifold. And here for all these results follow, we don't need any restriction on the dimension. So anything D bigger or equal than 1 is fine. And so this chart, what I call a boundary chart, satisfies the following properties. First, that P is at the center of this chart. Secondly, that I do have good control of the metric. So here this means that the metric is arbitrarily close, so delta close to the Minkowski metric, which is just the diagonal metric in these coordinates in this chart. And also I have a uniform bound on the Lipschitz constant of the metric G tilde. So recall that we have a Lipschitz extension. And now the important bit, the non-trivial bit, is that there exists a Lipschitz continuous function f, such that when I look at the graph of f, when I look at the graph of f, that is a Lipschitz graph. Here, this is the curve gamma. And so the statement is that the region beneath the graph of f, all of these points, they lie in the original spacetime. And all points on the graph of f, these are boundary points. They lie in the boundary. Yeah, so this is my notation here, that this is the graph of f, they lie in the boundary. And also that the curve gamma is ultimately contained beneath the graph of f. let me make a few remarks about this. So I don't make any statement about what happens above the graph of f. So here you see it could happen that the original spacetime lies above the graph of f. I don't care. I don't make any statements about this. And it could also happen that when you look at the boundary of your time and tilde, that there might be bifurcations here, so that you might have a different branch here of the boundary which bifurcates towards the graph. So the state is not that the boundary is locally Lipschitz regular, but I'm just saying that I have this region here below the graph and all these points that lie in M, and the boundary of this region, this is a Lipschitz graph. And in this sense, I say that the boundary of Lipschitz extensions of global hyperbolic spacetimes is Lipschitz continuous. Let me also make the remark that the proposition does not hold for C0 extensions. Yeah, and so it's not just that I don't have a Lipschitz bound. What fails in general is this non-trivial statement here that this curve has a limit point on this Lipschitz graph, so that to both sides I have boundary points. So this is a subtle issue. So here, in order to have this boundary characterizations, it's important that the extension is local Lipschitz regular. So this is the statement which addresses the issue A from before.
So wait, Sbierski, I have a question. So
Sure.
if you got rid of the assumption that gamma would be a causal curve and just was a time-like curve that hit the boundary, then it would be true for C0 extensions.
No. So the issue here is if I assume that this is a time-like curve, it might still, it might not be a time-like curve up to the boundary point. So if I assume that this is a time-like curve, it could have, it could not be differentiable at the limit point, or it could be null. So even if I assume that gamma is a time-like C1 curve, then I still don't get the statement for C0 extensions.
Okay, I see. Thank you.
Okay, so now we have like a class of spacetimes which naturally arise in the Cauchy problem in general relativity. So they're global hyperbolic, and I look at future extensions, and I have a characterization of the boundary, and I know that it's Lipschitz regular in the sense I've just described. So now let me come to the main theorem. Which I will illustrate for you again. So here we start with our time-oriented and globally hyperbolic Lorentzi manifold, where we need that the metric now is at least C1. And I have two local Lipschitz extensions, M tilde and M hat. And I again have my anchoring causal curve gamma, which has a limit point here and a limit point here in this spacetime. And then by the previous proposition, I know that there exist these charts U tilde and U hat. Such that the boundary is given by a Lipschitz graph so like this, and that the curve lies below the graph. And now the statement of the theorem is that there exists now smaller neighborhoods omega tilde, w tilde. So let me draw them here in the chart. Omega tilde and omega hat. Yeah, omega hat. Such that if I look at the identification map, and here the identification map just arises by going up iota tilde and going down iota hat. So that this identification map, this region here, is diffeomorphic to this region here. And this is here a notation that W tilde with by this I mean omega tilde intersected with the region below the graph of f, and similarly here for omega hat, so that this region here is mapped to this region here by the identification map. This identification map extends as a C11 log regular isometric diffeomorphism to the boundary, so to omega tilde with inequality or equal, and this is omega tilde with graph of f and everything that lies beyond below it. So this is the statement of the theorem, and let me make a few comments. So the first comment is that I told you that the boundary is the Lipschitz regular, but here I have the statement that the identification map extends as C11 log regular diffeomorphism. So of course, this is the boundary is not sufficient to make sense of C11 log, and so what we need to resort to is the standard concept of functions being smooth or differentiable on closed sets in Rn, and here definition of that a function is smooth on a closed set if it extends as a smooth function to an open set which contains the the closed set. And so here exactly what we're showing is that here this identification map from omega from here the region below the graph to this region below the graph, that this extends as a C11 log regular diffeomorphism to omega tilde, which maps omega tilde into omega hat. So it extends to a C11 log regular function from here to here. And since below the graph it's the identification map, and below the graph it's so, just by continuity, it of course extends to an isometry to the boundary, but in general not as an isometry to above the boundary. And the other comment I want to make is that if you assume more regularity on the extensions, so for example, if you assume that the extensions are C1 extensions, then you also gain regularity on the extension of the identification map. You always gain 1 degree of regularity. So if you assume that both extensions are C1, then the identification map extends as a C2 map to the boundary. Okay, and the next thing, so if there are any questions, please let me know about the formulation of the theorem. Otherwise, I will continue now to telling you about the promised counterexample that shows that we can't improve the statement of the theorem to regularities below local Lipschitz. So the counterexample is a cosmological 1 + 1 dimensional spacetime here with x coordinates, and g is given by -dt² plus 8t dx², where a is a smooth and positive function such that at goes to 0 for t going to 0, and also assume the existence of particle horizons so that 1 over a is near 0. And so, for example, take at t to the p with p between 0 and 1. So I want to now construct two extensions which have a regularity below local Lipschitz such that the state of the previous theory fails. So again, I mean, here again in this in the two-dimensional spacetime we have left and right going knowledge d6, and again we straighten out first the right going knowledge d6. So we introduce a new coordinate v like so, and also a new coordinate tau in this way, and you can check that in these coordinates, in the v tau coordinates, the metric takes this form, minus and so since a goes to 0, we can extend a as a function of tau to tau negative just by setting there identically to 0. And so if you choose at equals t to the p, then computation gives that then a squared of tau is proportional to tau to the 2p over p plus 1. And so you see from this here that if you let p go to 1, the metric disorder continues with any exponent up to anything less than 1. Let me now draw what the first extension looks like. So we again have these two families of nullity d6. Here in this one, I've straightened out the right-going ones, which are curves of constant, and intersect the boundary at tau equals 0 transversely, and the left-going ones, they look like this, and they become tangent to the boundary at t equals 0. This is the first extension, M Toda. And the second one I construct analogously by straightening out the left-going knowledge d6, and so I introduce these coordinates u and tau as before. Yeah, and the metric takes also the same form as before. Just u and v interchanged. And here in this second extension, I straighten out the left-going knowledge d6, and the right-going ones become tangent to the boundary at tau equals 0. And so what you see is that, first of all, these extensions, they are anchored by the same set of curves. So here, any of this knowledge d6 has a limit point in both extensions. But you already see that from the fact that here The right-going ones, they intersect tau equals 0 transversely, and here they intersect them tangentially. That's something with the differentiable structure must go array. And so you can see this by down the identification map, which again is a map here from m tilde to m hat. So here in the tau v coordinates from m tilde, it takes the form like this. Yeah, so this here is just u. And so you see that you look at the differential of the u component of the identification map with respect to tau. A straightforward computation gives that this is equal to a squared goes to infinity as tau goes to 0. And so this shows that the identification map, although it extends as a continuous map, and so the same curves have as an anchoring, the C1 extensions are non-equivalent. And so, for example, one manifestation of this is that if you have two observers, one enters the first extension m tilde, the other one enters the second extension m hat. The observer carries with himself like a normalized time lag vector, so normalized to unity, that you can arrange the following scenario to happen: that in one extension this time lag vector has a regular limit, and in the other extension this time lag vector goes to infinity. Yeah, and so it shows that you can't make a sense of an extension being the right one or the other one. Yeah, and this is something that can only happen in Lorentzian extensions. So if you have the analog for Riemannian extensions, if you have a vector which is normalized to 1, then it always, it cannot grow unbounded in one extension, and in the other one it remains bounded. And I see that my time is up. Actually, I wanted to tell you a bit more about the idea of the proof of the theorem, but oh no, I still have 7 minutes, right?
Yeah, you have 7 minutes because you started at 3:10.
Okay, good. Then let me tell you at least a few years about the ideas how to prove this theorem. Let me copy this. This cartoon here. So let me say a few words about elements of the proof. So here on the right-hand side, this was the setting. We had here the two extensions m tilde and m hat. We had this anchoring curve gamma, and then we have these two charts where space lies below the graph, and I know that the identification map here from this region to this region extends as a C11 log regular mapping to the boundary. So how do I prove this? The first step, what I want to do here in the chart U tilde, I want to go over from the curve I told I want to go from this curve to the curve of constant x bar. Yeah, so x bar labeled the last d coordinates, so the spatial coordinates. And so what I want to show, I use this new curve as an anchoring for a reason I will tell you in a second. But now the first problem that one has to circumvent is to show that also here in the chart you had that this curve here, this curve x bar equal to 0, that this actually has the same limit point here. It could a priori happen that this curve, goes to a different point or even leaves the chart or something like this. So what I want to do is I want to characterize when two inextendable causal curves gamma 1 and gamma 2 have same limit point in extension. And so in order to address this problem, I use actually a construction from the B boundary. So what I do is I show that there exists sequences Tn and Sn, which go to 0 for n going to infinity, and a sequence of curves sigma n such that sigma n0 is gamma 1 T1 and sigma n1 is gamma 2 Sn. So here, if I draw again a picture, here's my first curve gamma n, and here's the second curve gamma 2, which let me draw directly as the curve of constant x, gamma 2. So I have these two sequences, Sn and Tn, and these connection curves, sigma n, which connect gamma 1, 2. And these connection curves have the following property. If I look at an orthonormal frame field, so here alpha labels the vector in the frame field. So it goes from 0 to d, and I labels along which curve I have it, so along gamma 1 and gamma 2. So here these E alpha, these are parallel orthonormal frame fields along gamma 1 and gamma 2. Then the following two conditions hold. The first one is that the generalized affine parameter length with respect to the frame E alpha 1 of sigma n goes to 0 for n to infinity. So let me perhaps tell you, since if you don't know what the generalized affine parameter length is, so how you compute this is you parallelly propagate the frame field E alpha 1, which lives along the curve here, sigma 1. You parallel propagate this along sigma n. And then you expand the velocity vector of the curve sigma n with respect to this parallelly propagated frame, and then the generalized affine parameter length with respect to this parallel frame along sigma n is just given by the Euclidean length of the velocity with respect to the parallel frame. Sorry, the s goes out of the square root. Yeah. So this here is just the Euclidean norm of this vector here. Yeah. And this is the generalized affine parameter length of this curve. And secondly, that the parallel transport of E alpha 1 along sigma n is related to E alpha 2 by uniformly bounded Lorentz transformations. Yeah, so here if you parallelly propagate the orthonormal frame field from gamma 1 along sigma n to gamma 2, then you can, then at each point here, it is related to a Lorentz transformation to the parallelly propagated frame along gamma 2, and the statement is, what I want is that these Lorentz transformations are uniformly bounded. And so I show that you can find this set of connection curves, and this is something that will seem familiar for people who are familiar with the B boundary. And then in the second step, I show that this implies that gamma 2 must have same limit point as gamma 1 also in the second extension M hat. Yeah, so this was the statement up here. So indeed I have this picture. And so this was the first step, which I told you that I replaced the anchoring curve gamma by another anchoring curve, which is more suitable to me. And if I can just ask for 2 or 3 more minutes, then I'll tell you just briefly the idea of the proof. So now we have this picture here in our first chart, U tilde. I have here this anchoring curve of constant x. And I know that this curve also in U hat goes to P hat. And so what I do now is I consider like a family of space-filling curves, which are all of constant x in U tilde. And so here in the other chart, what I would like to establish, of course, is that these curves, that they also stay close to the original curve and end up at the boundary. But what might happen a priori is that these curves, they might also, for example, leave the chart and then hit the boundary somewhere far away. And so what I do is I now consider here a small hypersurface sigma in both charts. And I choose an orthonormal basis E alpha on sigma and parallelly propagate it along these curves. And so I know that initially here these curves, they must be contained in both charts. I mean, later on, as I said, they might leave. But so if I have here in this chart x coordinates and in this chart y coordinates, then I can write this parallel transport in terms of the x coordinates or the y coordinates. So here, if I parallel transport this orthonormal basis E alpha and express it with respect to the x coordinates, then I get such an expression. And here with respect to the y coordinates, I get such an expression. And since they're related by an isometry, I can write them as equal, just different coordinate expressions. And so now here, this is of course an invertible matrix. And so by bringing this over to the other side, I can write the differential, and this is in a sense the key idea of the proof. I can write the differential that relates the two coordinate charts in this form. Yeah, so I can write this in terms of the parallel transport with respect to the x and the y coordinates. And so now, since we have, recall from these charts that the metric as well as the derivative of the metric, this comes from the local Lipschitz bound, since these are uniformly bounded, I get that the parallel transport remains bounded. And so in particular, I get here that these matrices and also the inverse, that they remain bounded. And let me now conclude just by very briefly outlining the rest of the idea. So we have now that these coordinate differentials, which relate the two differentiable structures, that these are uniformly bounded, and using this you can show that these curves can't leave the coordinate chart. And what you then get is that these coordinate, the differential of this identification map, that this actually extends continuously to the boundary here in a small neighborhood of p tilde, and then you use standard theory of extensions of functions across Lipschitz boundaries. This is classical theory in analysis, and you show that if the differential of the function extends continuously, then actually the function extends in a C1 way. Yeah? And since you can also show that here those stay non-degenerate, you also get that this differential here when you approach p tilde also is non-degenerate, and then just by inverse function theorem you get a small neighborhood in which the identification map extends as a diffeomorphism. This is the rough idea. There are more details, but let me stop here. Thank you for your attention.
Okay. Thank